Extracting personality from text is one of the hardest problems in computational linguistics. Traits like openness or neuroticism aren't explicitly stated. They're latent, context-dependent, and woven into subtle linguistic patterns across long narratives. Traditional keyword approaches fail, and while large language models can process massive contexts, they bring their own baggage. Pre-training induces latent personality-like biases that make single-model predictions inconsistent and often skewed. A recent paper from Southern Methodist University and Washington University in St. Louis tackles this head-on with a fine-tuned multi-agent framework designed specifically for detecting the Big Five, or ocean, traits in life narratives. Instead of asking one model to guess your personality, they decompose the problem into specialized perspectives, ground the reasoning in psychometric theory, and use a hierarchical judgment system to arrive at a final prediction. Let's break down exactly how it works, the math behind the fine-tuning, and why this architecture actually outperforms single-agent baselines. The core idea is surprisingly elegant. For each of the 5 ocean traits, the system deploys 3 specialized subagents, one oriented toward high expression, one toward low expression, and one toward a neutral baseline. That's 15 subagents total. Each one is trained to recognize the specific linguistic and affective cues associated with its trait level. During inference, the transcript runs through all 15 agents. Each outputs a binary decision, supporting textual evidence and a confidence score. Then, a dedicated judge model takes all that structured feedback, compares the alignments against the original transcript, and synthesizes a final high, neutral, or low classification. But how do you actually teach a general-purpose LLM to think like a psychometrician? The authors use a combination of masked language modeling fine-tuning, low-rank adaptation, and psychometrically grounded prompts. Let's start with the fine-tuning. Rather than just feeding the model personality labels, they fine-tune each subagent using a self-supervised masked language modeling objective. Here, where it gets specific. 30% of tokens in each training sequence are masked. 15% are emotional words, identified using SenticNet, a large-scale emotion lexicon mapping words to 6 basic emotions like anger, fear, joy, and sadness. The other 15% are non-emotional structural tokens. By forcing the model to predict these masked tokens in context, the subagents internalize the emotional and syntactic patterns that correlate with high, low, or neutral trait expressions. To keep the fine-tuning efficient and prevent catastrophic forgetting, they apply low-rank adaptation, or LoRA. Instead of updating the full weight matrix, LoRA injects trainable low-rank matrices into the attention projections. Specifically, they target the QProj, KProj, VProj, and OProj layers. The task-specific weight update is parameterized as tau equals alpha over r times b times a, where r is the rank and alpha is a scaling factor. These updates are merged back into the base model, using the equation theta merged equals theta base plus lambda tau. In their experiments, lambda was set to 0.3, which empirically balanced retaining pre-trained knowledge while strongly adapting to trait-specific language patterns. Fine-tuning alone isn't enough to guarantee psychometric validity. That's where the prompt engineering comes in. Each subagent is grounded in the IPIP-NEO instrument, which breaks each of the 5 traits down into 6 lower-order facets. For example, neuroticism isn't just one thing. It's measured through anxiety, anger, depression, self-consciousness, immoderation, and vulnerability. The high agents receive positively keyed facet definitions. The low agents receive negatively keyed ones, and the neutral agents get a blended, moderate version of both. This gives the subagents explicit, theory-grounded lexical anchors to search for in the text, steering them away from generic linguistic heuristics. During inference, the subagents run sequentially in half-precision, clearing GPU memory between runs. They output structured JSON containing their binary determination, extracted evidence per facet, and a confidence score. This is where the judge model comes in. The judge receives the full transcript, the facet definitions, and all 15 subagent outputs. It doesn't just average votes. It performs a comparative assessment, checking how well each subagent's evidence aligns with the actual text, evaluating coherence, and resolving conflicts. The result is a holistic trait-level prediction with a concise justification. The architecture choice here is deliberate. They use Mistral-7B for the subagents and Qwen-2.5-7B for the judge. Why? Subagents process short, facet-specific prompts where Mistral's parameter efficiency shines. The judge, however, has to ingest the full transcript alongside 15 detailed agent outputs. That creates a substantially longer context window. Qwen's larger native context capacity allows it to aggregate that distributed evidence more stably. When they swapped to using Mistral as the judge, performance dropped, proving that matching model capacity to the aggregation task matters. The results back this up. Across the span life narrative dataset, which bins continuous personality scores into tercels, their full multi-agent framework achieves the best overall macro F1, improving by roughly 8% over the strongest single-agent baseline. Ablation studies reveal exactly which components drive this gain. Removing the IPIP-NEO facet keys causes the largest performance drop, slashing average F1 by over 15%. That tells us explicit psychometric grounding is non-negotiable for reliable evidence collection. Removing the MLM fine-tuning drops performance by 11%, and stripping the trait-level role prompts drops it by 10%. The decomposition itself, removing subagents entirely, still costs nearly 8%, confirming that specialized perspectives genuinely help. They also ran a semantic alignment analysis to quantify how well the subagents actually focus on trait-relevant evidence. By computing cosine similarity between each subagent's extracted evidence and the IPIP-NEO facet keys using a sentence transformer, they measured a directional alignment margin. The full model consistently produces the highest positive margins, meaning the agents are genuinely pulling evidence that matches the intended trait polarity. When you remove the facet keys, some agents even flip to negative margins, actively pulling evidence in the wrong direction. To visualize what the fine-tuning actually learns, they projected the LoRA task vectors into two-dimensional space using principal component analysis. The plot shows that subagents trained on different traits are well separated. Even different levels within the same trait, like high versus low neuroticism, form distinct clusters. You do see some expected proximity, like low neuroticism sitting near high openness and neutral extroversion, which aligns with known psychological covariation. This proves the LoRA parameters aren't just memorizing noise. They're encoding meaningful, semantically relevant trait adaptations. Let's look at a concrete example to see why this multi-agent reasoning actually matters. In a case study for openness, a single-agent baseline classified a participant as high openness based on surface cues like multiple career transitions, advanced education, and self-reported curiosity. But the multi-agent framework caught nuance. The high agent noted intellectual curiosity and varied roles. The low agent pointed out the narrative was concrete, factual, and lacked artistic or imaginative depth. The neutral agent acknowledged some exploration, but flagged the absence of novelty-seeking. The judge weighed these perspectives, recognized that the career changes were pragmatic rather than adventure-driven, and correctly assigned a neutral classification. Single-agent models consistently overinterpret surface mobility as personality traits. The multi-agent system forces the model to reconcile conflicting signals before committing to a label. Of course, the framework has limitations. The neutral class is consistently harder to classify, which makes sense given that moderate trait expressions are inherently ambiguous in text. The dataset comes from clinical life narrative interviews, which may not generalize perfectly to noisier, social media-style text. And while the multi-agent setup improves reliability, it does increase computational cost compared to a single forward pass. The authors also note the evaluation is currently English-only and IPIP-NEO based, leaving cross-lingual and cultural adaptations for future work. Ethically, they emphasize this is a research tool for understanding narrative patterns, not a deployment-ready system for high-stakes decisions like hiring or clinical diagnosis. This work demonstrates that reliable personality inference from long, complex text requires more than just prompting a frontier model. It requires decomposition, psychometric grounding, and hierarchical reasoning. By forcing the model to look at personality through multiple controlled lenses, you strip away pre-training bias and surface-level heuristics, leaving behind a much more robust and interpretable assessment. If you're working in computational linguistics, affective computing, or psychometrics, this framework is a strong blueprint for building more reliable, theory-aligned LLM systems. I've linked the full paper and supplementary materials in the description. Let me know in the comments which component of this architecture you'd want to experiment with first, and I'll see you in the next one.